Good morning. I, Sawan Patel, first of all congratulate you to enter in the same 5 of your BSc Mathematics. In this lockdown period, we are conducting online lectures. I will take Mathematical Programming MT5504. The textbook for Mathematical Programming is Optimization Methods in Operations Research and System Analysis by K.V. Mittal and C. Mohan. It is available in our office library, St. James College Library. This textbook contains text, the theory portion, and the problems we are going to discuss are from Operational Research by Nita H. Shah. At the beginning, I am clearing that you will get some disturbances in noise because my home is near to the road and natural atmosphere is there, so you will hear voice of birds as well as dogs and vehicles. First, we recall definitions and examples of linear spaces. You have studied linear spaces in your previous semesters. First definition is of binary operation. For non-empty set, a function f from x cross x to x is called binary operation on x. Let G be a non-empty set and plus be a binary operation on G. Then G plus is called a group if this following properties holds. First property is x plus y plus z should be same as x plus y plus z for all x, y, z in G. This property is called associativity. Next is there should exist zero element in G which satisfy x plus 0 is equals to x is equals to 0 plus x for all x in G. Here 0 is called identity element and this property is called existence of identity. Third property is for every element x in G there should exist y depending on x such that x plus y is same as 0 is y plus x for all x in our group. There should exist the inverse. This y is called inverse of x. If non-empty set G is given and binary operation is given which is satisfying all these three conditions, then G plus is called group. If G plus is a group, then it is called abelian group or commutative group if x plus y is same as y plus x for all x in G. Let's see a few examples. N plus n is stand for set of all natural numbers. Plus is our usual addition. Then it is not a group. due to the several reasons. First is there does not exist identity element in n for the operation addition, because for x plus y is always greater than x as well as y in n. But z plus is a group. Here z is stand for all integers. Here this is just for natural numbers. Here all integers means positive natural numbers, negative of all natural numbers, and 0. Here we know that 0 is an identity for addition, and for each x we know there exists minus x, which is inverse of x, such that x plus minus x is 0. Similarly, R set of all real numbers with usual addition, and set of all rational numbers with usual addition, set of all complex numbers with the addition you know, are abelian groups. Now remove 0 from set of all real numbers with usual multiplication. Set of all rational numbers set minus 0 with usual multiplication, and set of all complex numbers set minus 0 with usual multiplications are again abelian groups. We know all the properties of that. Here in these three, the 0 element is our real number 0. The identity element is 0. And in these three groups, the identity element is 1. Here, inverse of x is minus x. And in these three groups, inverse of x is 1 upon x. Again, minimum of x and y, maximum of x and y are commutative and associative binary operations on R, N, Z and Q. But with respect to maximum or minimum, none of these is a group, because if we talk about set of all real numbers, there does not exist identity with respect to the maximum as well as minimum. For n, identity for maximum is 1, but there does not exist inverse. And for the others, again, there does not exist identity element. Again, GCD and LCM are binary operations which are again commutative and associative on n and z. We know that this cannot be defined on real numbers. Again, we know that inverse does not exist as well as identity does not exist for GCD and LCM. For LCM, we are having 1 in n as identity element, but that does not exist inverse. So as well as n and z are not grouped under GCD and LCM binary operations. Set of all real valued invertible matrices of order n cross m is a group over matrix multiplication, and it is denoted as GLNR. We know the identity element is identity matrix, that is diagonal entries are 1 and all the other entries are 0. And inverse, we know how to find out the inverse of matrix. Those inverse are the inverse of with respect to multiplication. Set of all real valued matrices or order n cross m is a group over matrix addition. Here matrix addition is the pointwise addition. Matrix Aij is given and matrix Bij is given, then addition of matrix Aij and matrix Bij is all entries are aij plus bij. It is denoted as m n cross m r with addition. If n is same as n, then we usually denote it as m and r with addition. Rn means n product of r is a group under pointwise addition. Set of all Riemann integrable functions. If you do not know the word Riemann integration, just think about integrable functions on interval 0, 1 with pointwise addition is a group. Here functions addition is pointwise, so the 0 function f of x is equals to 0 for all x in interval 0, 1 will work as identity element, since any function f plus 0 function will be the function itself, and the inverse of the function f will be minus of f. Set of all continuous functions on any open set subset of R, or even any set subset of R, is a group under pointwise addition. Since we know that uh, if f is continuous, g is continuous, f plus g is continuous, so pointwise addition is a binary operation, and again 0 function will be continuous and will be treated as identity element with respect to the pointwise addition, and inverse of f is minus f, and if f is continuous, minus f is continuous. So all the properties are satisfied. Set of all n times differentiable functions on an open set X subset of R is a group. Since again we know that if f is n times differentiable, g is n times differentiable, then f plus g is n times differentiable. 0 function is infinite time differentiable, so 0 function lies in here. It will work as identity element since f plus g 0 function is f for all f, and inverse of f is minus f. If f is n times differentiable, minus f is n times differentiable. The set of all continuous functions on X subset of R is denoted as Cx, and set of all n times differentiable functions on X is denoted as Cnx. Let f be non-empty set and two binary operations are given on that. First is I am denoting right now as plus, and the other I am denoting right now as star. Then we say f plus star is a field if these following three conditions are satisfied. The first condition is f with the first operation should be commutative group with identity 0. Here I am mentioning the identity because I need this identity at the end. Now, removing the identity with respect to the first operation, and if this f minus 0 is a commutative group with the second binary operation, then with the identity 1, then we go for the third property, that this star operation should be distributive over this addition, this plus operation. Means x star y plus z should be same as x star y plus x star z for all x, y, z in F. If these three conditions are satisfied, then F plus star is called a field. Here, this order is important. If we are replacing plus by star and star by plus, then this will be changed. The first condition that f star should be commutative group with respect to the some identity, and removing that identity for the second binary operation it should be a commutative group. So, and again this third property will be changed because here it comes second binary operation, here it will come first binary operation. So this order is important. Let's see in the example itself. We know that z plus with multiplication is not a field. We know z plus is a commutative group with identity 0. It is satisfied. But for the second, uh, removing that 0, so z minus 0 is not a commutative group with respect to the second binary operation, multiplication. Since 3 lies in z, but the inverse of 3 with respect to multiplication does not lie in z. Okay, but we know that set of all rational numbers, set of all real number, and set of all complex number with usual addition and usual multiplications are filled. We already have seen that q plus r plus and c plus are commutative group. Removing 0, we know that whenever x lies in q, r or c, 1 upon x lies in q, r or c. So inverse exists. Identity element is 1 with respect to the multiplication. Hence they are filled because the third operation is always there, multiplication is always distributive over addition. See here, if I interchange the order q with multiplication will not be filled. Q with multiplication comma addition will not be filled because Q is not a commutative group with respect to multiplication because the inverse of 0 does not exist in Q. Similarly for R and C. Set of all invertible functions with pointwise addition and pointwise multiplication is not a field. Invertible functions, by that I am meaning functions with so that f of x is that and 1 upon f of x is defined, means f is not 0 on the given domain, then it is not a field because f function f is there, then with pointwise addition its inverse is minus f. Addition of both uh, will be lie passing through 0 function. We know at least one function we can define which is passing through 0 and it will not have multiplicative inverse. Here by integrable functions I am meaning that integrable functions on interval 0 1. Set of all continuous functions on x subset of R with pointwise addition and pointwise multiplication is not a field. Again, see f of x is equals to x is continuous. That function will work well in integrable functions also. So f of x is equals to x is continuous, but 1 upon f of x is not continuous. So inverse with respect to the multiplication does not exist. So it is not a field. Now we think about the other fields. So the set of all rational functions on R means functions of the form polynomial divided by polynomial is the field with addition and multiplication like rational numbers. Now moving towards the vector space. Let V be a non-empty set plus b binary operation on v, and this dot is a function from f cross v to v. This much is given. Here f is a field with 1 O plus and O multiplication with identity 0 and multiplicative identity 1. Then V plus dot, here this V plus this dot and this field. This pair is called vector space over F if following conditions satisfied. First, V plus should be an abelian group. Next, with respect to this multiplicative identity, this dot should work properly. Means 1 dot x should be same as x for all x in V. Then this dot should perform well in this way that alpha scalar, this dot is called scalar multiplication. So I will now denote it as scalar multiplication. So alpha scalar multiplication with beta scalar multiplication with x should be same as multiplication of alpha and beta with scalar multiplication with x for all alpha and beta in F and x in V. Now this scalar multiplication should be distributive over vector addition. Means alpha scalar multiplication of alpha with x plus y should be same as addition of scalar multiplication of alpha with x and scalar multiplication of alpha with y for all x, y in V and alpha in F. Alpha plus beta should scalar multiplication with x should be same as alpha scalar multiplication with x plus beta scalar multiplication with x for all alpha beta in F and x in V. This is called scalar multiplication is distributive over field addition. So if V is given with binary operation and field, then it is called vector space if these 5 conditions are satisfied. Let's see a few examples. Let V be Rn with pointwise additions. Then, and scalar multiplication of course, multiplied to the each and every term of xi. Then Rn is a vector space over field R. Again, if V is Cn with the similar operations, then it is a vector space over field R as well as over field of C. Now I am saying that field R is a field and C is a field, means it is a field with usual addition and multiplication. Now onwards, wherever R with as a considered as a field and C as a considered as a field, then it is clear that it is with usual addition and with usual multiplications. Set of all continuous functions on interval AB, real valued continuous functions on interval AB. I already have told that I will denote it as C AB with pointwise addition and multiplication defined in this way. Alpha multiplied with F evaluated at x is alpha times F at x. Then V is a vector space over a field R. Let V be n times differentiable and nth derivative is continuous functions collection with usual pointwise addition and scalar multiplication again defined in as previous, then V is a vector space over field R. You can verify all this at your home. Set of all n cross m matrices with real entries with matrix addition and scalar multiplication defined is again in a similar way that alpha is multiplied to each and every entry of matrix, then V is a vector space over field R. Again, if we consider entries from instead of real from complex, then again it is a vector space. But here, this is a vector space over field R as well as over C. Let V plus dot be a vector space over field and S be subset of V, then it is called linearly dependent if there exist finitely many elements in S and those finitely many scalars in F minus 0 such that its linear combination, we know that this is called a linear combination. So its linear combination alpha 1 x1 plus alpha 2 x2 plus alpha n xn is 0. Here now I am not mentioning that it is here multiplication is scalar multiplication and this is a vector addition. You know all these things, so I will not mention now onwards if it is not required. Here, make sure that 0 is an additive identity of F, means a field, and this theta is an additive identity of vector space V. So set is called linearly dependent if using non-zero scalars we can write at 0 element of V as a linear combination of vectors in your given set S. If it is not there, means the set S subset of V is not linearly dependent, then we will say it is linearly independent. That is, for no choice of xi in S and scalars alpha in F minus 0, we can write theta, means identity of V, as a linear combination of xi and alpha I. Means whenever we try to write identity of V as a linear combination of elements in S, then we end up at alpha I is 0 for all I in this collection 1 to n. Again, here 0 is identity for field and theta is identity for V. Let's see the example. R3 is a vector space over R. We already have seen. Then S, collection of these 4 elements 1 0 0, 1 1 0, 0 0 1 and 2 3 1 is linearly dependent. Why? Because subtracting this from here we get 0 1 0 and using the linear combination of 1 0 0, 0 1 0 and 0 0 1, we can write 2 3 1. So 2 3 1 can be written as linear combination of previous 3 vectors, and hence 0 0 0 can be written as difference of these two, these 4, and we end up at 0 as a linear combination of these four vectors without using 0 as a scalar. So it is linearly dependent, or you can try your at home. But if we think about these vectors 1 0 0 0 1 0 and 2 3 1, removing this 0 1 0 0 1, then it is linearly independent set. You have studied how to prove this set is linearly independent and dependent. Now let S be subset of vector space V over a field F. Then the span of S is the set S such that alpha 1 x1 plus alpha 2 x2 plus alpha n xn, where alpha i's are in F, xi's are in V, and n in N. Means choose finitely many xi from your vector space and finitely many scalars from F, and their linear combinations collection is span of S. We will denote it as box X. Sometimes if we require, then we will denote it as S star. Let V be a vector space over field F. Then the set S subset of V is called the basis of V if S is linearly independent and its span is V. You have studied several examples of bases. Let's see a few. We have seen that this set is linearly independent. Oh, sorry. 0, 0, 0 is already there, so it is linearly dependent because we can write 0, 0 as 1 times 0, 0, 0, and hence it is linearly dependent. But you can prove that 1, 0, 0, pi 1, 0, and 0, 1, 0 is a linearly independent over field of rational numbers. You try this at your home. If you cannot do that, we will discuss in the discussion form. Let M2R be set of all 2 cross 2 matrices with real entries. Then this set, first matrix is 1 2 3 4, second matrix is 1 0 0 2, and third matrix is 0 2 0 1, is linearly independent. To check this set is linearly independent, first of all observe that M2R can be seen as R4, just writing by 1 2 3 4 in one row. Similarly, 1 0 0 2 in one row and 0 2 0 2 is in one row, and then you know how to prove that this set is linearly independent. Again, if you cannot do that, we will discuss in discussion form. Try this again, that this set is linearly dependent. Let's set up all continuous functions over interval 0 1 as a vector space over R. Then the set 1 x x square x cube is linearly independent. I think you have discussed or studied in your previous semester to prove how to prove that this is linearly independent and dependent. Again, if you cannot do, we will discuss in our class. But if we think about set of all continuous functions on interval, instead of interval 0 1, on the set 0 1 and 2, means in this set we are having only 3 points, then the similar set 1 x x square and x cube functions collection is linearly dependent, not independent. So this set's linear dependency or independency is depending on the vector space. Okay. If we think about set of all continuous functions on interval 0 to 2 pi, then you actually can prove that 1 sin x, cos x and x squared is linearly independent, and this will be a very good job if any one of you will do and submit it in our exercise form. Let V be a vector space over F and x1, x2, x3, x4 is linearly independent, then the set x1 plus x2, x2 plus x3 plus x4, x3 plus x4 and x4 minus x1 is also linearly independent. You can make several such other sets which can be treated as linearly independent. Now moving towards the inner product. You might have seen or not, but for the theory portion of mathematical programming, this inner product is very much important. So if you could not get the examples and solutions of linearly independent dependent sets, though for the theory portion, if you are want to have 100% in exams, at least one theory will be in the first question based on this inner product and that previous linear convex combination. So now onwards focus whatever is going on. This inner product is very much important in several ways. You will require to think about this inner product. Uh, Several good discussions can be based on this inner product on any linear space theory. So function from V cross V to R satisfying these conditions. First of all, non-negativity for same pair x and x. So inner product of x and x should be non-negative for all x in V. If inner product of x and x is 0, then x should be 0. And if x is 0, this inner product should be 0. Inner product should be distributive in addition in this way that inner product of x plus y z is x inner product of x with z plus inner product of y with z. Here plus is by mistake, it should be comma. X inner product of x with y should be same as inner product of y with x for all x, y and v. And inner product of alpha times x comma y should be same as inner product of alpha times inner product of x with y for all alpha in R and x and y in V. Here I am taking V as a vector space over field of real numbers. That's why this alpha are from real number. If this function with these 5 properties is there, then we say that function as inner product and V plus with this as an inner product space. Let's see an example. V is Rn is a vector space over R with inner product defined as inner product of x with y as summation of xi by I is running from 1 to n, then it is an inner product of Rn. Since first property is obvious, summation of xi into xi means summation of xi square is always non-negative. If summation of xi square is 0, then we know that each and every xi square is 0 because all the terms are non-negative and its sum is 0. So each and every term xi square is 0. That implies xi is 0, means x is 0 element in V. And again, if x is 0 element, then 0 times 0 is 0 and its summation is 0. So second property is obvious. Third property uh, is again obvious if xi plus phi times zi is xi times zi plus phi times zi, and hence the third property. Again, product of xi yi is same as yi times xi, so fourth property is followed, and alpha can be scaled out from this addition. So Rn with this is an inner product space, and we will deal with Rn only, specially for mathematical programming. So we will be with this inner product only. But I am discussing several other things related to inner product. Norm, a function from V to R satisfying four conditions. 1. Norm of x should be non-negative for all x in V. Norm of x is 0 if and only if x is identity element of V. Alpha times x should be same as mod of alpha times norm of x for all x in alpha in R and x in V. And norm of x plus y should be less than or equals to norm of x plus norm of y for all x and y in V. This fourth property is called triangle inequality. If such norm function exists satisfying this four condition, then we say it is a norm, and V with this function is called norm linear space. Let's see an example. V as Rn and x is x1 up to xn, then define uh, x bar sup norm. We say this as a sup norm be the maximum of mod xi. And another one, norm of x1 should be is defined in a way that mod of xi summation I is equals to 1 to n. You can prove that these two are norm on Rn.
We stop day 1 here. You are supposed to complete all exercise given in this lecture. Exercise should be uploaded on Moodle on next Monday. Thank you for listening this lecture. Don't be panic, stay at home, stay safe. Wishing you a healthy life.